Hey everybody, this is a video about the sunbeams or the sun rays that come through the clouds called crepuscular rays. And what I'm going to do here is prove in this video with a series of proofs beyond a shadow of a doubt that the sun is close and the sun is small. First I'm going to show you an experiment I did with the sun rays that's very solid proof that the sun is in fact close and not very big. And then I'm going to refute Wikipedia's account of these crepuscular rays. They say that these rays are due to perspective and that in fact they are, for all intents and purposes, parallel lines from a sun that's almost 1,000,000 miles in diameter. But the fact that we see them splaying out, they say that that's due to perspective. I'm going to show that that's impossible. And then number 3, I'm going to show that it's actually when you take a look at this picture of the crepuscular rays, that actually perspective is missing from this photo, if in fact the sun were 1,000,000 miles in diameter and 93 million miles away. The heliocentric model is in trouble. So let's get to my experiment. I watched a video from my perspective. His video is called Flat Earth Sunbeams, Part 1. I was outside and I go, man, let me try that. And I just kind of ran in, I grabbed some cardboard, I cut some holes in it, and I wanted to see how the sun reacts coming through. So here I am, raising it high over my head, so I'm about 8 feet away from this, and the light doesn't diverge or spread out. You know, it doesn't splay out like we see the crepuscular rays. And this sun's far away. Just like in the heliocentric model, the sun is far away, right? 93 million miles away from our clouds. But we see the sun rays splaying out from the clouds as though it were a close sun and not a faraway sun. Well, you can see when it is far away, the light beams are parallel and they don't splay out or diverge from the clouds. So then I got a little bit more sophisticated. I went inside and I cut some nicer holes in another cardboard. You know, my budget went up. And here they are, and I put some CGI here. I put some beams in there, and you can see they are dead straight. No splaying out. And then you can also, there's a part here where I have it up overhead and I had the same results, no splaying out. So this is the example of the far away sun, that the rays, this is what we should experience coming through the clouds. The rays from a sun that's almost 1,000,000 miles in diameter and 93 million miles away, when those rays get here, they should be parallel and dead straight. But we don't see them as dead straight. We see them splaying out or diverging from the clouds. Something's not right here. Okay, here I am inside. Notice I got my light close. Look at already you can see the light splaying out. You see that? I drew you can see the circles on the floor and on my piece of cardboard actually. Those are the original size of the holes that when I was outside they lined up perfectly. Here you can see them completely splaying out. And if I put the rays on it like this, the sun rays, and that's not even as splayed out as they got, it's just that the cloud is in view. And I want you to be able to see the cloud, which is my cardboard with the holes cut out of it. That way I could line up the rays. But as you can see, when I moved up a little bit off the floor and put the light even closer, the rays really splayed out. So I just wanted you to see that. Okay, so there you go. There's hard evidence that when the light source is close to the clouds, the light will diverge. The dispersion pattern you can see when I was outside, the dispersion pattern remained the same, meaning the 5 holes that I had, that stayed exactly the same, and that's a faraway light source. But when the light source was close, they splay out. That definitely supports the flat Earth model of a small, close sun. Okay, let's analyze this claim that science makes and Wikipedia makes that the crepuscular rays are due to perspective, that they're actually very close to parallel lines. For all intents and purposes, they are parallel coming from a sun that's almost 1,000,000 miles in diameter, but we don't see them parallel coming through the clouds. Those crepuscular rays are angled outward. They splay out. They're diverging from the clouds. And Wikipedia is saying that that's due to perspective. Okay, and Wikipedia also uses railroad tracks like these. And they say, see how these converge at your horizon, or they diverge from the perspective of the sun outward? And they're saying that that's what's going on here. Okay, so we need a quick little review of perspective. Notice in this long hallway, All parallel lines and planes angle to the eye level or the eye position of the observer. Notice that the side walls angle in, those are parallel lines to one another, and the ceiling and the floor are also parallel, but notice how they angle toward each other and they come to your eye level. All right, you have an X, Y, and Z axis. So the railroad tracks would fit your Z axis. That's going away from you, and those lines, yes, they converge. But the sun, and especially when the sun's overhead, would be bombarding us with huge vertical parallel lines, or rays, parallel rays. Yet, we don't see any of that, ever. So what I'm going to show you here is that this claim that these crepuscular rays is due to perspective is not true. It's impossible, because perspective will not converge or diverge or splay out lines or planes that are parallel to one another, that are perpendicular to the viewer or his z-axis. Okay, so like in this picture of the railroad tracks here, the line's going away from you, that's I did with the green line, that's the railroad track, that's obvious. And right from the get-go, they start to converge. Now those are parallel lines, but yet we never see them as parallel. They're always converging as they go away from you. Now the black poles that I have going down the side of the railroad tracks are also parallel lines to one another. But notice that they stay parallel. They don't lose their parallel orientation. They may get shorter and they get smaller, that's true. They do have a sort of a convergence, but they don't change their parallel orientation, these vertical lines, because they're perpendicular to you. Now, this is why invoking perspective to explain the crepuscular rays doesn't work, because perspective does not splay out these vertical lines, yet whenever the sun is overhead, we should see vertical parallel rays everywhere, and yet we don't see them. So perspective as an explanation for this is invalid. You know, what we see is the rays emanating from this omnidirectional sun. The rays fit the size of the sun, and the angles of the rays off the sun also fit the size of the sun and the shape of the sun. But they shouldn't fit the size of the sun if the sun is in fact almost 1 million miles in diameter and 93 million miles away. The rays should be huge and the sun small. So that's telling us that the sun is in fact close. Okay, and let's go back to what Wikipedia said. Wikipedia says that the rays from the sun are in fact parallel lines, but we don't see them that way because of perspective. Perspective splays them out. Okay, look at this picture. I put these rays in. Okay, so this is what's really going on, Wikipedia says. They say the rays are really parallel, and they would be from a 1 million mile diameter sun. But this is what our eyes do through perspective. It splays it out. Okay, here's another one. They say this is how they really are. They're vertical and they're parallel, but our eyes splay them out like this. Okay, so then why doesn't perspective take these telephone poles and splay them out like this? We don't see that, do we? Why doesn't it take these buildings and splay them out like this? They're vertical and they're parallel. Well, because what we see, the crepuscular rays, is not due to perspective. It's just due to the nature of an omnidirectional light source with the light coming out in all directions. And it's coming from a small sun. It's impossible that this sun is 1 million miles in diameter, as I've already showed you. So then if it's not perspective, these crepuscular rays are not due to perspective, as Wikipedia and science in general claims they are, then what are they? Well, it's very simple. All they are is radially propagated light. Or another way of saying it, light rays emanating out from a common center, like the sun, or any light. And I understand that the light rays coming off the sun looks like perspective. It shares the common trait where, with perspective, all the lines and planes converge at a point in the distance called your vanishing point. The sun also has that look, where looks like the rays all converge at a point in the center of the light. Actually, the light rays are emanating out from a common center, but I can understand how they look alike, but they're not the same. Okay, that's all it is. And so, as we've already proved, that perspective can't explain the crepuscular rays, because where are all the vertical parallel sun rays then? They don't exist. Okay, so next I'm going to show you with street lights and sunlight and how they look exactly alike. Okay, let's take a look at some light rays. Let's look at how the sun and a street lamp look the same. The one on the left is a street light and the one on the right is the sun. Okay, notice that the light source and the rays match one another. And with the street light, that light is here on Earth, right? It's right there on your street. And those rays look in proportion to that light. They're also here, right? On your street or wherever you see that light. The sun, they're telling us, is actually far away, but the light rays are close. Like when we see these crepuscular rays coming through the clouds. And did you know that streetlights also have crepuscular rays, just like the sun does? And you know what? They look identical. Let's have a look. Here on the left, that's a streetlight, and those are crepuscular rays coming off of that streetlight. And they look identical. They are in the same proportion as our sun and its rays. And you can't say that that's perspective because they're right there. And as we've seen, perspective can't explain those rays anyway. So those rays are nothing more than radially propagated light. In other words, it's light coming from a common center. That's all. And look at this one. The left one is a street light. The one on the right are the sun rays. They are both in proportion to one another. The light source matches its rays, which indicates that they're both local. Okay, and this street light is here. We know it's here, and we know those crepuscular rays are here. There's no fooling us and telling us it's 93 million miles away or a million miles in diameter. And it looks just like the sun, that they're telling us is far away and huge, and whose light rays are here, though, on the Earth. Same here. Same as what we see in the sky. The sun matches the sun rays. But in the heliocentric model, with a sun that's 93 million miles away and almost a million miles in diameter, the rays should be completely out of proportion, like this. You know, we shouldn't maybe even see the sun. Maybe the sun should just be a blob of light on the other side of our lit up atmosphere from these huge rays. I mean, we see the sun like it's in our atmosphere, like it's close, but it can't be, according to the heliocentric model. And next, I want to show you how, in this photo, perspective is actually missing. And what's ironic is the very linear perspective that they tried to invoke to explain this photo is actually missing from this photo for the heliocentric model to be true. Okay, so what do I mean by that? Well, I mean they invoked perspective to describe or explain these crepuscular rays, the fact that they're splaying out from the clouds, because they had to invoke perspective or something because this picture doesn't work for the heliocentric model. This picture of these crepuscular rays is a problem for their model because the sun is supposed to be a million miles in diameter. But the problem is they've invoked perspective, but perspective doesn't work because, as I've already showed you, it doesn't explain the parallel vertical lines that we should see all over the place. Perspective will not splay those out, right? So these vertical rays should be everywhere, the parallel vertical rays, but we don't see them. The perspective that's missing is like the sun is out there and it's almost a million miles in diameter, right? So its sunbeam, it shoots out a sunbeam, and that sunbeam is 100,000 miles wide, let's say. But what we see from here looks very small, right? But not when it gets here. When it gets here, it's going to be massive, okay? But yet, look at these sun rays coming through the clouds. They're small, they're skinny, they're tiny. They match the local sun that we see in the sky here. So that's what I mean by perspectives missing. And let me give you a couple of real-world examples to help you figure this out. Okay, now imagine you're at a football game, an American football game, and you can see the player, the quarterback, down on the field, and he's as big as a peanut, okay, on the field, even smaller. Okay, and the football is the size of a short grain of rice. And he's got this great arm, and he turns around and he throws that ball up to you in the stands, and he can throw it all the way to you. Now, I got a question for you. When the ball gets to you, is it going to be the size of a grain of rice, or is it going to be the size of a regulation football? Well, it's going to be the size of a regulation football, right? But that's not what we see in this picture with the sun rays. Those sun rays fit the size of the sun. And now let's take a look at this soccer player. All right, for those of you who don't know American football, there, he kicks it, he's far away, and the ball gets to you, it's going to be the size of a soccer ball, right? This is proper perspective. This is the perspective we're not seeing when we look at the sun. The sun that we see in the sky is close. Okay, here's a train leaving a station far away down the tracks. Also analogous to the rays leaving the million-mile diameter sun. Okay, the rays would be massive just like the train is massive compared to that little train station. Right? That's proper perspective. Now look at these shafts of light coming from the sun, the rays. The sun on the right here, each of its rays that you see coming off the sun would be about 100,000 miles wide, just like this. You could fit 10 Earths side by side in that ray. Okay, so when we look at these rays, they're not 100,000 miles wide, and they're diverging out from a small sun that we see in the sky. I mean, that proves right there the sun is close and small. Now, I know somebody's going to seize upon this and say, hey, wait a minute, but we don't see perspective with the sun traveling over the flat Earth. We should see it shrink to a dot and disappear. We don't see that. Well, I was going to save this for another video, and I maybe still will, but let me introduce to you celestial perspective. It's different than regular perspective that we're used to every day. Regular perspective, we see a train on the tracks, and as it goes away from you, it gets smaller and smaller and smaller until it disappears. But the sun, on the other hand, is different because the sun, when it's quote-unquote next to you, is high overhead and has already experienced a reduction in size. Now, as it goes away from you, it follows the convergence lines down to your horizon, essentially keeping its same distance from you. So the two movements offset each other. The one, the sun moving away from you, and then the visually lowering as it follows the convergence lines down to your eye level horizon. Also, the sun is too big to shrink to a dot anyway, right? It's going to go below the observer's horizon before that happens. Now note this about the convergence lines. Notice that on this wall of lines, the higher up they get, the more steep they get. They orient themselves away from the horizontal and more to the vertical. So the train on the tracks, as that goes away from you, it's right on your eye level. It's actually on your z-axis. Here's a picture of the z-axis, x-axis, and y-axis. It's on your z-axis, so all you can see is the train get smaller and smaller and smaller. You can't see any movement laterally or vertically out of that plane. But the sun is different because the sun, even though it's cruising over the Earth parallel to the ground, it's on a much higher plane. So when it's overhead, it's already had a visual reduction in size. So now when it goes away from you and it follows those convergence lines down, it'll appear to be the same size because the going away and the lowering kind of offset each other. And same as this train. If you put this train high up overhead, that will cause it to already have a visual reduction in size also. So now when it goes away from you, it too will maintain its size. Kind of like if you're flying a kite, right? And you have the kite and it's a mile overhead, well, it'll appear a certain size, right? But let's say it takes a nosedive, but the string stays taut, so it goes all the way to the ground. Now it's a mile further down the road from you, but it's still the same size visually, right? So that's kind of how this works too. So let's recap. In my experiment, I showed that when the sun is close, the rays splay out, but when the sun is far, the rays are straight parallel beams. Yet, this is what they show us, this picture of crepuscular rays, and say that that's a faraway sun. Then I showed you how perspective can't explain what we see because it doesn't splay out things like these poles or these buildings. And then I showed how the sun mimics perspective. It has the same look. The light rays radially propagate outward, or they radiate out from a common center. And that's what we're seeing with the sun. It's not perspective. And then I showed how the streetlights, the crepuscular streetlights, match the sun. The same crepuscular rays from the sun and from the streetlights, and they look identical. Both local light sources and local rays. Then I showed you celestial perspective, and that's different from regular perspective, like the train going down the tracks that's on your same plane as your eyes, and as that goes away, it can only shrink. It gets smaller and smaller. But the sun is high up overhead, so it's vertically already had a visual reduction in size. So as it goes down to your eye level horizon, it'll maintain its same size. Okay, and that wraps up celestial perspective, and that wraps up this presentation. I believe we made a strong case. A lot of evidence here, if not complete proof. And thank you so much for watching. There's only one thing left to do. Let's kick the ball out of here. Take care.